Thank you so much, Sebastian, for giving me a chance to come here to share with some of the research we have been doing. So this is a joint work with my long-term colleague, Peter Forsyth, and a postdoc, Peter Van Standen, who actually currently he would return to Australia, at Australia for National Bank of Australia. And then my two graduate students, Mark, who is remotely there somewhere, and Mohab. Okay. Yes, Peter is there too. All right. Okay, so here's a very quick outline of my talk. So I'm going to describe the class of problem I'm interested in solving: a discrete time, finite horizon, optimal control problem. And I'm going to talk about a new approach that we've been following that is using neural network and with the policy function approximation, but without dynamic programming. And I'll give you some justification theoretically as to why that is a good thing to do. And the essential idea, one of the essential ideas is using neural network to represent the stochastic control. And then I'll focus on a particular problem. It's called the decumulation problems. You have problem, I have problem to pronounce it too. And I will define the problem and describe the objective function and the constraints that need to be imposed. And this is one of the very difficult problems to solve. And so I want to talk about why the approach actually works, and in particular the difficulties that with the problem that computationally our method is able to do a very good job. I hope to be able to show you that, and I'll conclude. Okay, so here's the framework. We have a time horizon, and mostly I'm interested in long-term horizon, 30 years investment horizon. And we are looking at a stochastic optimal control problem. And basically, we're trying to make decisions at each of the time points, n time points, let's say 30 years every year. And our goal is to pick the control or the sequential decision so that it's optimal in some objective. And so, for example, it could be based on the terminal wealth of your portfolio. And so the objective function could be generally stated as basically we are trying to find optimal control so that the conditional expected rewards, some function of the reward of the wealth, think about it, is minimized. And so this objective basically encoding the risk and the return in some measure. And here I describe the problem as like objective functions based on terminal wealth at the end of 30-year horizon, but you can generalize it to path dependent reward calculation as well in the objective function. Okay, so this discrete stochastic optimal control problem, in fact, encompasses a lot of interesting problems in finance, including pricing American option, the decision of whether to exercise or not, option hedging, delta hedging, and so forth. And so, and naturally, dynamic asset allocation. And this is a class of problem we've been focused on. And so essentially, think about the horizon where young people here, and you will need to retire 30 years from now, and how you can accumulate your money so that you have enough money to retire, right? And the defined benefits, pension plan is disappearing, and this defined contribution, which means you have to manage your money well and wisely. And for those of us who are older, and we will be faced with, okay, suppose we worked long enough, got a large portfolio of, let's say, $1 million, how do we withdraw without running out of money? Okay, how do we manage my money? Okay, so that is a very relevant problem facing a lot of people in all different countries, right? Because defined benefits is just going out of the window, and defined contribution becomes everybody's pension plan. And so in particular, in this talk, I'm going to look at the decumulation problem. So some of my earlier work will look at the accumulation problem. So in this talk, I'll focus particularly on the decumulation problem, and towards people who are older, who has built a large portfolio and needs to make sure that you have enough money before you expire. Okay, so and William Sharp had called this decumulation problem the nastiest, hardest problem in finance. And let's see whether that is true. Okay, so here is think about our decumulation problem, right? So in this context, essentially, what we are going to do is that we're going to we have a large portfolio. Let's say at time 0, we're going to withdraw money from our portfolio. So the QN denotes the amount of money I'm going to take out, withdraw from my portfolio. And at the same time, I need to wisely invest in my assets. And so I will be having so in addition to withdraw, which is one of my control, I will need to allocate to invest stocks and bonds in some optimal fashion. And so as you can see, for this decumulation problem, we have a pair of control, dynamic control, and withdraw and allocation that needs to be considered at the same time. And if you think about your investment is to multiple assets, and you're faced with this dynamic allocation problem and withdrawal problem in high dimensional case, like I don't know, could be interested in factor investing or just even long-term, short-term bonds, and then different market indexes and so forth. So the problem quickly do become potentially large and long-term horizon, and it's difficult in that sense. Okay, so how is this class of in general dynamic optimal control problem solved? Typically, we have a parametric model approach. We build a stochastic model on the asset returns for the long-term horizon. And so we estimate a parametric model based on historical observation. And one of the difficult with this approach, the parametric approach, is that, well, the parameter is difficult to estimate, depends on how many parameters you have, right? But computationally, this is also a challenging problem to solve because we have sequential decisions needs to be made optimally, and very typically, the computational problem is solved through what is called value functions, which essentially give you a attach the value when you make your optimal decision optimally at each of the rebalancing time of your investment, right? So typically our optimal policy search, optimal decision search is guided by a set of value functions defined at each of the discrete time events and rebalancing time. And so, typically, dynamic programming is a very popular computational technique that is used to help us find optimal decision, because it basically decomposes the sequential 30-year decision time to one at a time, right? So that's the idea of dynamic programming, converts multi-step optimization into a single-step optimization problem. And indeed, that's kind of the principal idea behind all those class of PDE approach for solving this problem, right? They use the Bellman's principle to change the problem equivalent into some kind of PDE equation solve. And you can, but the problem with 3D is that when you go high dimension, you cannot solve it. There's curse dimensionality, exponential time complexity that becomes into the picture. And then if you think alternatively, okay, let's do some kind of simulation-based approach. And that's similar idea, very at a high level of long step short idea for American option pricing. And then indeed, that's a approach that's been considered in the literature. And the difficulty with this type of approach, in fact, some of the reinforcement learning method falls into this category as well, based on simulation, but use dynamic programming to help with the decision, finding the optimal decision. And as you can imagine, the difficulty with this type of approach is that if it's multi-step approach, you have value function, they are approximated, and there's a potential error back propagation issue. So that's stability becomes one of the problems, right? So the question is, okay, what do we do? How can we solve this kind of problem? Well, I guess what a simple idea is that, well, let's go back to the original problem we're trying to solve. Originally, we have a 30-time-year horizon problem, a single optimization problem defining my optimal decision. So if I go back to there, if I imagine that I have a long-term horizon, 30 years long-term horizon, I have many paths of assets returns being given. Suppose I have scenario paths of a path trajectory, return trajectory being given. And then I approximate my problem, original optimization problem through essentially discretization in the state space, then this is a problem I'm going to be faced with. I replace the expectation by empirical average, right? And so then that will be the problem that I would need to solve. And how would I solve it? Well, I know that my rewards, the wealth, is sequentially being updated by the formula I showed you before, right? So then if I just think about it, I have all those price trajectory or return trajectory going forward, then I'm trying to determine the optimal decision for every rebalancing time, for every price or return trajectory. So the problem is that, and that's a huge problem, right? A single optimization problem, every state time discretization, I have an unknown. But then naturally we think about, okay, what I just approximated this control by functions of state variable, right? And so basically through approximation of my control, I make assumption of my control, which is function of time and state, and make some assumption about this control function. Then I change the problem into a finite parameter optimization problem. And that indeed is a class of a method that has existed before called policy function approximation problem. Without dynamic programming, we solve directly the problem there. However, historically, typically the function that's used is very simple, quadratic and so forth, but naturally, one think about with all the machine learning, let's just use neural network for those policy function, right? So that is indeed a natural way to think about this problem. So essentially, we can change this difficult single optimization problem and using neural network to represent the policies or the controls at different time, different state, right? Then I change my difficult problem, very large problem, into a finite number of parameters for my control function problem. So somehow I will be able to simplify my problem and solve it. So let me just describe this more formally. So what's the basic idea? Well, so imagine that I have so what I'm trying to do is I'm going to solve this problem without using dynamic programming. So what I need is that I will need a function approximation to the control, right? Which basically is because I approximate the control by a parameterized control function, parameterized by theta parameters, think about it as neural network. And then basically then my problem becomes a finding the parameters of neural network so that I optimize my objective function. So that's all seem to be very natural and intuitive and simple. And indeed, if we further to say, okay, I'm going to really computationally solve it, and I'm going to assume all those return trajectories, different scenario being given, then I also, my problem becomes this scenario-based single optimization problem I'm going to solve for to find the parameters for my control function. If I use neural network, then that will be neural network parameters. So, okay, that all seems to be very intuitive and simple. And indeed, it's an idea basically using the neural network to approximate the control function to solve those optimal decision problem has been taken even in the field of finance over years, and this is by no means exhaustive literature listing as well. So yeah, we can see many works basically follow this idea using neural network to represent the control function you're looking for by solving a single optimization problem, the original optimization problem, without using dynamic programming, right? So this is some list of some work that has appeared in the literature, and I just point out a bit difference between some of the work that for example, the early work by Heng and Yi, with our work, that is that because our control is at every rebalancing time needs to be determined. So we actually use a single control function instead of using a set of control function at every rebalancing time. So that's one of the difference that what we do. Okay, so all right, to basically, yeah, so the problem becomes very natural. We approximated the original problem using neural network and to solve single optimization problem, original optimization problem without using dynamic programming. Is that, what does this approach give us? Why is that a good thing? Well, besides the fact that the error back propagation issue, potential instability issue, theoretically, this approach actually makes a lot of sense. And so, in fact, essentially what it's happening here is that, okay, if you think about this stochastic optimum control problem, right? And if you follow the dynamic programming approach, you're going to require value function at every rebalancing time. And that value function is obtained by optimizing over a control of a conditional expectation, which is high dimensional, where so using dynamic programming approach, you will need to compute conditional expectation at every rebalancing time over what is called a performance criteria, which is this conditional expectation, and the dimension of that function, the conditional expectation, is number of assets plus 1 if time is one of the feature variable. So if you look at a high dimensional investment, then you're looking at high dimensional conditional expectation function you are trying to estimate. However, so you can show that for those kind of problems, for stochastic optimal control problem, we're considering the optimal control function itself is in fact actually no dimension, right? So it's the optimal control function is actually a function of time, and state in this case it's just the wealth at rebalancing time. So it's a low dimensional optimal control we're trying to determine. And so that basically says that there's a single neural network approach solving the long-time horizon problem essentially exploits the low dimensionality in the control function. So that's advantageous from the computational complexity perspective. Okay, all right, so that's some theoretical justification. Okay, so we're going to solve this problem by looking at scenarios, many scenario paths. How do we do that in practice, in real world, right? In financial market, we usually only have a single time series observation of market return. So suppose back to, you can go back as far as 1926, and so we need to return data. We have return data from 1926 to 2023, for example. We don't have many observations of the data. If we use monthly return data, I mean, that's only very limited observation, right? So in academic literature, we look at this optimal control problem. Traditionally, typically, we assume a parametric model, for example, some kind of jump distribution model, double exponential jump distribution model, and we estimate parameter for the parametric model from this one single path, right? That's one way to do it. And then you can generate simulations from your estimated parametric model. Alternatively, practitioners, in fact, like to use what is called a resampling of market data. And they use this, they just basically sample the market observation, resample them, block resample them, generate different possible permutation of market regime, if you like, to augment to generate the market data for doing the assessment of the trading strategy. So resampling of market data is a way to get scenarios from practice. So when we solve this scenario-based single optimization problem, essentially we can incorporate the industry practice of block resampling to generate different scenarios based on market data observation, right? So that's one way to do it. And then alternatively, yeah, you can do, if you like, you can estimate your parametric model, generate your different possibilities into the future. So our proposed computational approach, of course, you can generate data in either way, right? And we've done, in our previous work, we've done some of using block resampled data from the market observation to give us data. But in this work, I'm going to talk about here, we're going to actually use the parametric model function approach to simulate data and generate it. And what the reason is because our purpose here is really trying to assess how accurate this very simple seemingly simple approach is going to give us the solution. Okay. All right. So what I would like to address is that, can this very simple intuitive approach of using neural network to approximate control and then not using dynamic programming solve your optimal control problem? Does it work? Can you find good solution? So that's what I was going to do. And for that, I will put it into test by looking at the nastiest problem in finance, look at the dynamic decumulation problem. Okay. So the problem is that basically, imagine a scenario, I'm 65 years old, retire with a defined contribution, accumulated a large amount of money, and he's planning to live for another 30 years in investment horizon of 30 years, right? The industry standard, the popular industry standard rule of thumb to do this is just it's called Bengen's 4% rule. Withdraw 4% from your portfolio, and then allocation 50% stock, 50% bonds. Very simple. And apparently, if you just look at scenario being generated by the rolling historical data for 30 years horizon, you're never going to run out of money. So that seems to be a very good strategy. So that's called Bengen's rule. And so the question is, can we do better? Can retirees do better? Right? Can we actually really try to make sure we don't run out of money and withdraw sufficient large amount of money? So can we actually devise an optimal withdrawal so that we can maximize total withdrawal and minimize the risk of running out of money? And the problem with the Bengen's 4% rule assessment is that you only look at the historical scenario of 30-year rolling windows, right? And what if things don't repeat in that way, right? So it's not a complete assessment of the performance. Okay, so for that goal, we want to do better. So what we can formulate the problem. So we want to maximize expected withdrawal and minimize the risk of not getting enough money. So our objective function is basically a component of maximize reward, expected withdrawal, that's reward, minimize running out of money, shortfall. And there's a third term here. It's a regularization term, and that is that if you have accumulated so much money, in fact, you can have choice of doing something differently depending on what you want. That when you have you already have achieved your goal, right? And what do you do? So there's a stabilization term we add to further improve the performance potentially. Okay, so that's our optimal control problem. It does look difficult, right? There's nested to optimization, and our control here also it's a pair. There is a withdrawal and there is allocation, allocation, and so the shortfall basically is looking at the worst alpha percentile of outcome. It's like if you think about it's this negative CVAR, if you like. We basically maximize the tail on the left. That corresponds to minimize the worst case of scenarios. Okay, all right. So that's our. This is trying not to run out of money, trying to maximize the expected waste draw. And also we impose the constraints. So for our allocation, we don't want to short, we don't want to leverage. So there's some simple constraints for the allocation. And for withdraw, we also has some different constraint, which is kind of quite complex at the first glance, right? Basically, we said we want to withdraw has to be between an interval of a minimum amount and maximum amount. I want to withdraw to be in that range. Give me some. So basically, I say if my portfolio is larger than Q max, I want my withdraw to be in this interval. If my withdraw is less, I mean, if my wealth is very small, it's less than Q mean. In that case, I just only withdraw the minimum amount. Okay, so if the wealth is large enough, I have a range. I can choose to withdraw in this interval. If the wealth is less than the Q mean sum bound, that's the Q mean, the lower bound I'm going to withdraw. And if I'm within this interval, I'll allow more leg room. My control can be Q mean to the maximum of Q mean and the wealth. Okay, so this is if you think about it, it's a reasonable reasonable way I can expect my withdraw to be. So in any case, this is the constraint I want to impose on my withdraw. Okay, but if you look at this constraint is actually somewhat complicated because it's stochastic. My constraint depends on the wealth and the different wealth state value, different constraints being imposed. Yes.
If you don't have Q in wealth, how do you withdraw Q?
Sorry, Q mean is given. So I specify how much minimum I have to withdraw this much.
But if you don't have that much wealth.
Very good question. Can I get back to you? Okay, then that I have a discussion about that, but let me wait until there. Okay, so my wealth negative. How am I going to? What am I doing here? Basically, I say. Okay. All right. So okay. So that's the problem I'm going to solve. Looks nasty, complicated, right? And so, but we're going to just use the approach we propose. We will use a neural network to represent a decumulation control and allocation control, and I'm going to use a sigmoid activation function for the input and the output layer. Sorry, for the input layer, not output layer. Okay. Yeah, the last output layer. I should be. Okay. This shouldn't be output layer here. Okay. And my input, the input feature for my neural network will be just simply wealth and time, a single neural network for decision at all different time. Okay, so here's the thing. I said there are constraints for my withdrawal and allocation, right? How does a neural network handle that? It turns out that I will show you in this case, I can basically add a specially designed output layer. I can encoding all the constraints. I'll show you how I do that in a minute. Okay, so the neural network is fairly simple, 2 hidden layers, 10 nodes each for the withdrawal and the allocation control respectively. Okay. Okay, here's something, well, this is the work. How well will this work, right? So in continuous rebalancing setting, okay, the optimal control, optimal withdrawal problem, the control is a bang control. It means you either withdraw Q mean or Q max, bang, okay? So that's just what we know. And in the discrete rebalancing case, the withdrawal control is also approximately bang. Okay, so the control is discontinuous, okay? All right, so can neural network produce such a optimal control, right? And so how do I do the constraints? My constraint is stochastic, it depends on the wealth. My constraint interval is even different. How do I do that? How accurate the solution will be, right? Very simple idea, simple way of trying to solve this complex problem. Can I get accurate solution? Also, the important question we want to investigate. All right, so my first thing is, okay, let me describe to you how I'm going to deal with the constraint, okay? So basically, the constraint, the complex constraint, interval constraint I have imposed here can simply be encoded by a special function at the output layer. So if I assume my Zx to be the output of the neural network before the final output layer, right? And then, so that's my Z, that's output for my neural network. I'm going to add another final output layer. And then I just define my Q, which is a withdraw, to be this function of neural network output Z. Okay, so that's basically this a shifting and the scaling adjustment in this factor and the sigmoid function. Okay, so you can easily verify this simple encoding actually is able to is equivalent to this constraint we have for the withdraw. Right? You can easily verify if Q is less than, or if wealth is less than Q mean, this will give you Q mean and so forth. So you easily algebraically verify this does generate that. Okay. And the allocation constraint is simpler and it can be encoded in similar fashion. All right, let's put it into testing, see if it really will work. Okay, so we'll look at this computational setup. We have a 65-year-old retiree. I have 30 years to planning. Is started with $1 million of portfolio, and he's going to yearly rebalancing, withdraw, and allocate investment strategy. And we're going to put Q mean to be 35,000, and Q max be 60,000. And we fit our parametric model, jump diffusion model, to the historical past, start from 1926. And we use jump diffusion model is fit into the CRISP cap-weighted stock index, 10-year treasury index. And so we use data from 1926 to 2020. And the data is all just for inflation using the CPI index. And inflation is really important, relevant in this day of life. Okay, we're going to generate 256K paths from our estimated jump diffusion model, and we put our stabilizing term parameter epsilon to 10 to the power minus 6. Okay, so we're going to test our solution approach by compare the HJB equation approach. Because in this case, we're still at a low dimensional case. So the HGB equation approach, you can think about it as a proxy for an analytic solution, if you like. It's computationally, you can prove numerically it's convergent to the true solution, right? So that's basically what we're going to do. How am I doing in time? When I finish?
Finish around 7.
7 minutes. Okay, all right.
No, you have, let's say 12 minutes.
12 minutes. Okay, I can slow down a bit. All right, if there's any question, please investigate. Please ask me and I will get back to your question in a minute. All right, so let's first say if this neural network we are considering 2 layers for the control of withdrawal and 2 layers for the allocation of stock and bond, and the final layer to encode the constraint and its sigmoid function. Okay, can it actually produce accurate withdrawal function, optimal withdrawal function? Well, so here is the heat map of the withdrawal from the HJB equation. Right, it's a Bengen control 2-color, right? So this and the neural network without dynamic programming using the policy function approximation approach, the heat map, you cannot see the difference, right? So it's able to generate this discontinuous control, Bengen control, optimal control. Okay, all right, so that's good. Okay, we're further testing it so if you look at my optimization framework, where there's a kappa parameter, which is the weighting of your reward and risk, maximize the expected withdrawal, minimize the risk of running out of money, 5%, the tail risk we're trying to minimize. And so we change different kappa parameters. So those are those numbers on the on top of the nodes are kappa parameters, different risk awards, weighting or balancing, and we produce the efficient frontier. So the blue dots are from HGP equation, solving the HGP equation numerical approach, and then the neural network approximation is the orange dot, and you can see that in this case, the efficient frontier is being reproduced fairly accurately, right? So it's, I mean, I'm a bit surprised that it's capable of doing that, given that it's based on a set of scenarios going into 30 years, and we approximated the control at every rebalancing time by this simple shallow neural network and approximation in different ways using the, so in any case, it shows that it's capable of producing accurate results. Okay, so that's the efficient frontier showing for different allocation, optimal decision, how well it has matched the HGP equation. So here, what I'm trying to show is, let's fix kappa equal to 1, right? Actually, the Bengen control one is also for kappa equal to 1 for a particular point on the efficient frontier, where the weighting of the running out of money and the withdrawal is equally weighted with kappa equal to 1. Okay, so this is the optimal allocation strategy heat map. On the left is from HGP equation, and on the right is from the neural network solution. Okay, and so if you look at this, you might say, well, they don't look very much, they don't look quite the same, right? There's a lot of more difference. How come? And why the efficient frontier matches so well still? And okay, so the question is, well, the heat map don't look that much the same. How could the solution be accurate? What do I mean, right? So, but fortunately, we have this quantile file, the quantile curves on top of the heat map, and that can help me explain. So basically, this 95 percentile is the curve of allocation at different time at the 95 percentile. Oops, sorry. No, sorry, let me back up. Okay, so for most of the scenarios, this is the medium case. If you compare the medium allocation, that's basically the median average allocation, if you like, median, right?
Across scenarios?
Across scenarios,
so
yes.
You have a bunch of scenarios.
This is different. That's right. That's right. This is a median allocation curve, and that's a 5% allocation curve, and that's 95%. So if you compare between median and 5%, oops, sorry. This area here looks very much the same, okay? And so the difference comes mostly from upper here, 95 percentile when you have actually had enough wealth higher wealth accumulation. And in there, the effect of the top right corner actually comes from the stabilization term, really, mostly. And so that's a small percentage of time. And so there's because the epsilon is so small, that term's effect is very minor. So you can have the two different solution approach actually has smaller effect, and they don't affect the statistic of your performance significantly. So that's why that what is important is the scenario that's around here, right? It's between 5 percentile and this area, and then the allocation of the stock and bond allocation strategy are actually quite similar. Okay.
Because after 30 years, we don't want to be rich. We want to
you want to spend enough money. Yeah, that's right. That's another worry, different worry. Okay. Yeah. So in any case, I think those are the plots that shows that indeed this simple policy function approximation using neural network without dynamic programming actually is able to solve this very difficult nested problem. And so let me just further compare to the Bengen's 4% decumulation rule. So if you assume that 1,000 K initial wells, and if you test the strategy not on the rolling 30-year historical horizon, but on the block resample, the different scenario, different permutation of the market past, right? This Bengen strategy actually will have the expected shortfall of minus 270K. And then for our optimal strategy, this expected shortfall running out of how much money you're running out of, if you like, is minus 50K. Okay, so what this is saying is that the larger the left tail is better, right? So by the optimal decumulation formulation produces a strategy that will cut the probability of you running out of money significantly. So that's what it will show. Okay, so going back to your question, right? If you don't have money, your wealth is negative, how can you still withdraw? Here's the assumption, and it's a reasonable assumption, right? So it's our assumption you can withdraw, continue to withdraw even you run out of money. But why is that a rational thing? I see you already agree with me, right? So basically, we're assuming that you can do that because very often people have put a mortgage in their house. By the time they retire, they paid off their house, so they have real estate already, and they don't consider the real estate as part of their investment strategy. And so basically, in that case, you can in fact think of as a backup plan. If you absolutely, I mean, this is a very low probability case where you'll be running, the wealth become negative. You need to, but then in that case, maybe you can refinance your money, and that is justification for that consideration. Okay. All right. So yeah. So another question people might ask is that, you know, we measure the risk of running out of money by using CVAR or expected shortfall, and then we're doing this dynamic optimal control problem. And some of you may know that is not a time consistent strategy, and it's pre-commitment strategy. And what we feel is, our argument is that is not a concern. So pre-commitment strategy basically means you compute this strategy, but later on may not be optimal according to your original formulation, right? So, and our argument for adopting this is that it's okay because really this time pre-commitment or time inconsistence is when you are really looking at an objective, but there's an alternative interpretation of that objective function, and that actually, for that problem, your strategy is equivalent to a different objective function, but it's actually time consistent. So that's just a matter of opinion as how you interpret your objective function, if you like. Okay. And so just one final note, all the results investment consequences, all the quantities are adjusted for inflation if you're worried about interest rate keep going higher and higher. So that's what. Okay. All right, let me just conclude. I think what I hope to have shown is that the sequential dynamic finite horizon problem, it is a challenging problem from the modeling perspective, from the computational perspective, on many time horizon and the potentially higher dimension. And in fact, we do look at the investment allocation for more assets case. And the traditional approach, most popular approach, suffer some difficulties, and in particular, if you use dynamic programming principle, your computational approach will involve conditional expectation of high dimensional functions, and that can be difficult to do when you use simulation-based computation, and there's also potential error propagation. And the neural network policy function approximation approach essentially go back to the original problem, don't use the dynamic programming, instead exploit the fact that the control function is actually a function of a smaller number of state variable, exploit the no dimensionality in the control function directly and try to solve it, right? So, and it involves some of the potential issue of dynamic programming, and for particular this nasty decumulation problem, we illustrate that this simple computational approach using neural network, no dynamic programs, is able to handle the stochastic adaptive constraints that's imposed on the withdrawal, and is able to produce Bengen control, discrete optimal control, and yes, and the accuracy in the efficient frontier were produced in comparison to the PDE approach, which you can think of as a proxy of the mathematical solution. And I think there are more future work needs to be done, would be interesting to look at, and it's really also assess the accuracy of our computed solution, how robust it is, and to consider more assets, and also learn it directly from resample data, and maybe involving factors in our allocation strategy investment. Okay, well, thank you, and I will be happy to answer questions.